Okay, hello everyone. In this video, we'll be looking at solving an exercise where we're asked to design a decision procedure for a decision problem about regular languages. The decision problem that for which we're trying to design a procedure is the DFA is empty decision problem. So in the DFA is empty decision problem, the input is a DFA M, and the output, well, the output is always yes, no, but the expected output is for the decision procedure to return yes or return true. So to return true or to return yes if the language accepted by the DFA is the empty set, and it should return false or no if this is not the case. So if the DFA accepts at least one string over the entire alphabet, whatever that alphabet may be. So we can just assume that it's not empty in this case. Okay, so there are actually a few decision procedures that one can think of. The easiest one, though, is actually quite elegant and just relies on the fact that there's a very simple DFA that accepts the empty set, right? So the simplest, and what we would actually say more technically or more formally, the minimal DFA, which accepts um, the empty set, which accepts sigma, is the following. So it's essentially just going to be the DFA with a single state that loops for every letter in the alphabet. So that loops on itself for every letter in the alphabet, right? So this is the simplest DFA that one can design that actually accepts the empty set. Why is it the simplest or the minimal DFA? Because the FAs cannot have zero states. They have to have at least one state. And so this one has exactly one state. So you can't build anything that's smaller that accepts the same language. And also the other argument here is just because um, minimal DFAs, minimal DFAs are unique, right? So there's no FA that has a smaller number of states than one. This FA has a single state, so it has like the minimum number of states a DFA could possibly have, and it accepts what you want, right? And we have a theorem that says that minimal DFA are unique up to the relabeling of the states. So that means that whatever other minimal DFA you could think of, it would always look like this, basically. So why is this useful? It's useful because suppose you just start with any DFA, right? So you have any DFA M. It has a start state, it has other states. It might have accept states. I'll let you think of how a DFA which actually does not accept any strings, could still have an accept state. But in any case, suppose we have a DFA M, and we want to know whether it accepts the empty string. So in other words, that it does not accept any strings. So one thing that would not work is doing something like, so one procedure that would not work is for W in sigma star, run M on W. If M accepts W, return false. false because that means that it accepts at least one string. And once this for loop is done, you return true, right? Because if this for loop ends and you never went to the body of this if statement, that means that you ran all possible strings in sigma star and none of them actually got accepted by n. But this is kind of problematic. Why is this problematic? Because this for loop runs forever, right? So I actually have an infinite for loop here. Infinite for loop, which means that even if the machine did not accept any strings, you would actually just be stuck here waiting for maybe, the string where waiting for a string that actually satisfies this condition, right? So you're never going to be able to exit this for loop and get to the true. So this is definitely not going to work, regardless of the DFA, actually. So it could be any DFA. This algorithm is actually always going to loop forever if the answer to the decision problem is yes, right? And so instead, what we can do though is, well, we know that we have a minimization algorithm, and the minimization algorithm returns the unique minimal DFA, which is equivalent to the DFA that you started with. So that means that I can take a DFA M, I can feed it through the minimization algorithm, and then I'll get some new DFA M prime. And then I can check, right? I can just check, is it the same as this DFA? And this I can do in like a finite number of steps. It doesn't require like an infinite for loop. The way to check whether um, a DFA that's been converted, that's been minimized using the minimization algorithm is equal to this DFA is, well, it has to have three conditions, right? It has to have um, the size of the set of states has to be one, right? So if I just have like a transition table as the data structure to represent the DFA, then I just check that I have a single row. The other thing is that the set of accept states should be empty, right? So I can also check that because you can imagine that this information is like stored somewhere in my table. Maybe I have a star next to the states that are accept states. So I also check that there are no stars that sort of index my table. And the third thing is that I have self transitions for all um, the letters, right? So self transitions for Q naught, right? So if I have a table like something like this, not A, B, then, I check that there's no star here. So I check that there actually isn't a star here that indicates that this is a final state. I check that there's a single row. And I also check that if this is the name of the single and the only state in my table, then I check that I also go to that state for the entries A and B if the alphabet is AB, or for every single letter in my alphabet. So I check also that upon reading A, so if you wanted to do this programmatically, you could just go through all of the uh, output states for every um, input letter in your transition function and just check that, so you would just check that delta Q naught sigma is equal to Q naught for every sigma in the set of letters, right? And so this could be a very tiny for loop, which would definitely terminate because the alphabet has to be, this is kind of a definition in formal language theory, the alphabet has to be finite, right? So this is another thing that's kind of important to mention. The reason why you don't get an infinite loop anywhere here is because assumed sigma is assumed to be finite. Otherwise, it's actually impossible to have an FA if the alphabet is not finite. Okay, and so hopefully that convinces you of this sort of general sketch that I've created of the procedure where it's, you take the DFA, whatever it is, you minimize it, then you get a resulting DFA M prime. It's in terms of like, we don't have to sort of write down how the data structure would look like, but it would probably be a table or something to that effect. And then you can very easily check whether or not um, that table represents this DFA. So all of these are kind of like finite time computations, which means that I have a finite time algorithm. So if I write this a bit more formally, but still in pseudocode, so not that formally. Uh, let's write algorithm for decision problem DFA is empty. So on input, so the input is of type DFA-M. What are the steps that our algorithm is going to take? So we'll run the minimization algorithm on M, and then to get M prime, and then we'll check if M prime is equal to uh, this guy, for every sigma. Check if this. So if it is, then we return true. Else we will return false. Okay. This is good enough if you're writing pseudocode. It's definitely good enough to write something like this because it's we can argue we can argue very quickly like I just did here. So once you argue very quickly that it's possible to check that a DFA is equal to the DFA that looks like this, the self loop non-accepting DFA, then you can just add this as a line in your if statement because it sort of conveys what's going on in the actual procedure. And so if this is true, then that means that you actually did, to begin with, have a DFA-M which did not accept um, any strings just by the correction of the minimization, by the correctness of the minimization algorithm. Otherwise, then you return false because that means that um, you have a machine which doesn't look like this, um, but it's a minimal DFA. And so that must mean that it can't accept the empty set because if it did accept the empty set and it's a minimal DFA, then it would have to look like this. So because it doesn't look like this, then it can't be, it couldn't have been a DFA that did not accept any strings to begin with. Okay. And so this is um, a decision procedure. There are a few that one can think of, but this is one that decides whether, given a DFA-M, it accepts the empty set, so the set that does not contain any strings.